I'm a sort of social professor in computer science at the Trobe, and so I lead a group of deep learning students and postdocs or research assistants, and we work on mostly computer vision tasks and so apply to different kind of applications. And we, in general, like to work with applications that have real world impact and not so theoretical, very practical.
How did you get into AI? Like, what was that moment that went, huh, I want to do
And
something with this?
10 years ago, one day was just randomly looking at a YouTube video by Andrew Ng. So he's one of the really first, almost like godfathers of AI. And he just gave a really good presentation and just thought, oh, this is really exciting area. It seems a lot more fun than optimizing databases. The good thing about working at university is that you can just do research in anything as long as you write papers. So I then went back to my research group and said, I think this is more fun than working on databases. And all the students, it wasn't that hard to convince them. They all agreed. And then I started to learn about it and then teach my students. I was invited to this statistics group in Melbourne University to present, what I knew about deep learning. And there was a lot of other people, maybe, I don't know, more than 100 people from all around industry who came to watch that. I think in 2015, not many people really knew about AI or deep learning, and they all thought it was really exciting. So then I taught at the data science meetup in Melbourne, which had like more than 300 people, and then a lot of people got interested in it. By presenting it to so many people in industry, I got a lot of people who wanted to work with me. Um,
Okay, so that's how you got your
so
first projects. Yeah.
yeah, my first project, the most and still probably the highest impact work is with the Australian Institute of Sport. So I went to the Australian Institute of Sport, gave a talk. I went there in person, but that also they have all the people around Australia. I was able to watch this online. So that was the first exposure for a lot of the people in the AIS to this idea of AI and deep learning and how powerful it is for computer vision. So straight after that, they came up with different projects that they would like me to work on because I was the only one that they knew how to do this stuff. Two projects that came along. One was a swimming competition analysis project, and the other one was a diving sort of training, a program that where you monitor the training for divers and just to make sure that they don't have too high a workload. So with the swimming one, it's a project that they've actually already worked on for many years, but before me, everything was done manually. So there was no AI. They had computer software. What they want to do is in swimming competitions, the coaches have certain race plans that they give to their swimmers, and they want to know if the swimmers actually stuck with the plan and then maybe make adjustments during the competition because they have different rounds in the competition. And so specifically, they were very interested in the stroke length of how many strokes it takes for a swimmer to go from one side to the other and things like that. And so in the past, they would have a sports analyst, which would use a camera zoomed in each swimmer, and then they would capture that video and then upload this to a software. Then they would need a person to basically press spacebar every time the hand goes down and touches the water and things like that. When they had Australian championships, they would literally have a table where they would have maybe 8 or 10 analysts all just pressing spacebar until late into the night to annotate all of this data, which then would be available for the coaches the following day. So this was very time consuming and also error prone. So that's when I got involved. Initially, I got a small seed funding to just test out if AI can do this kind of stuff. This was our very first project, and fortunately, I had a very good student called Brandon Victor who was working with me at that time. He was able to somehow figure out how to code the thing and use our GPUs. We bought them GPUs and things like that. So after about 3 months, we had a working prototype and we were able to get something like 96% accuracy with, I don't know exact numbers, but it's very high. And then when we presented that to the AIS, they were very happy and it seemed like this thing can work. So then we applied for a larger, I think it's called the Competitive Innovation Fund at the AIS. It's a competitive grant, and we were awarded this to build an actual production version of this software. And then we basically, instead of having a single camera per swimmer, we then changed our idea to have one camera for the entire pool for all 8 or 10 lanes. So
Wow.
that, yeah, that makes a big difference because it means it's not only efficiency that you can do multiple lanes, but it also means that you can do the opposition as well. So you can analyze what the opposition is doing, and if they're performing better than you, what is the difference, you know? So we did that. And then instead of just doing stroke length, we also wanted to get the instantaneous velocity of the swimmer. So as they're swimming, then we had to get a lot of data to be annotated by the people in the AIS, but they provided that support. And yeah, so we were able to show that we could make it work on these 4K zoomed out videos, but we need a lot more annotations and for different lighting conditions, sometimes even outdoor pools and things like that. So we were able to get that working, but then I think to make it work from like a prototype to a production version, that's like another huge step. And so even though we had something that worked pretty well, maybe within a year or something, but to make it work in all different kinds of conditions. And it turns out that the actual software, the front end, is actually quite complicated. So as we were trying to do these things, we got more and more requests of new features. We kept having to add things, and we also had to do the bulk of the front end development. One thing I want to just mention also was that it's very important that we had stakeholders in the AIS and Swimming Australia, which really believed in what we were doing. Even though it didn't work very well in the initial stages, they stuck to it. And they were also very aware that they don't want to give coaches anything until it's very good because the coaches don't really like things that not work well. And they're also maybe more suspicious of AI, whether it's accurate and things like that. So they had to select the ones that are more really believe in this a bit more than the others. But then they also waited until this product, they were refined it a lot before they started to present it to the coaches. I think it took about 2 years since when we first made that first prototype before we could make something that was stable and good. But that was through many iterations of trying to come back with us with new features and telling us what went wrong. And but fortunately, we got there in the end because of the 1 year delay on the Tokyo Olympics. So we were able to make it in time for the delayed Olympics. And yeah, so the good thing is all the competition analysis in Tokyo Olympics was done using our software. Actually, specifically 2 high-power laptops where we bought them for them and using the grant, and then we installed all our software. We also made sure that we could remotely debug it if anything went wrong. And fortunately, nothing actually went wrong during the Olympics. So the laptop, yeah, was able to do all the pulls. We can process that near real time, so it's not exactly real time, but maybe in a couple of hours after the competition finishes, we can have all the results and things like that. So that
Wow,
was
that's quite
yes,
fast. So
yes,
they've gone from having maybe 8 people
yeah,
and 8 cameras
yeah,
and then waiting till the next day really to get the
yes,
results and not
yeah,
really getting competitor information to having all of the competitor information, all of the swimmers within a couple of hours.
yeah,
That's big. And you were saying
yeah.
they also used it at the Paris Olympics?
Yes, so after the Tokyo Olympics, and they proved that it really worked well, Swim Australia decided to use that for every international and national competition from that time onwards.
Wow. And it didn't require you to continue to monitor it live or anything. It just works. It's quite stable
Yeah.
now, or?
So to be honest, once it became really stable and it worked really well, our team at La Trobe just effectively handed it over to the AIS. One lesson is that you need to have a champion for this thing in the industry because it's not going to be smooth sailing. At the beginning, things didn't really work. And we also needed a lot of work from them to annotate the data. And we shouldn't make light of that. That required a lot of organization. And also they had to pay people to do the annotation. But that was only possible because we had people there that believe this thing can work. So, and also, yeah, and then doing that final stakeholder engagement with the coaches, they had to be really careful that they don't want to show off something that only half worked. So that was, I think that these are things that you normally don't really think about. And actually, when we just made that first prototype, for most research I've done up to that stage, that would be normally the end, and we would be patting ourselves on the back. But then it's like another 2 years of actual work to make it go and be reliable enough to use in practice. So that's something I learned, which I didn't know that would be such a big gap to make a prototype versus a production software.
So true. Commercializing research takes a lot longer than you think. Yes.
Yes, that's right.
So tell me, what are some of the projects you're working on now?
I'm working on quite a lot of different projects, but probably the most dominant one at the moment is on digital pathology. So imagine if somebody's been diagnosed with cancer, they have their tumor removed. So then what happens every time when the tumor gets removed, the oncologist needs to know what is the situation. So they basically take the tissue, slice it up, and then look at it under a microscope. Typically, a pathologist would then grade the cancer, stage the cancer, has it spread, to effectively give an estimate on the prognosis for the patient, like how likely the cancer is going to reoccur. Once we've taken the tumor out, is it basically solved the problem? It's not going to come back, or is it maybe potentially going to come back? So based on these kind of information, an oncologist would then make decisions on how to treat the patient with chemotherapy, which we know has a lot of adverse side effects. So they would normally only treat if they think it's necessary. Or nowadays, very commonly, they use immunotherapy, which is very successful. But even for that, it doesn't work for all patients. So only certain patients it works for. But in the end, pretty much all the information that are needed by the oncologist to make these calls are all resides in the tissue that was extracted. But in the past, you would have pathologists which would look at these manually through their eyes and quantify what they're seeing. And for example, looking for certain type of cells and how dense it is, like immune cells, how much immune cells and so on. We've been working with some people in Austin Hospital and ONJ to basically use AI to replace or to help assist the pathologists so that we get these tissues scanned by a digital sort of scanner. And then we use AI algorithms to do the kind of the tasks that the pathologist can do. And we've shown that we can get very similar results with pathologists in terms of the ability to predict the prognosis for the patient. Is the cancer going to come back or not? But yeah, so there's certain advantages of using AI for this because every pathologist it turns out it's a fairly subjective task. What looks like an immune cell to one person, to another person, it might look like a tumor cell. So two different trained pathologists might make contradictory calls because they actually look quite similar. Then it becomes less reliable. Depending on which pathologist, you might get a different density of these immune cells. But the good thing about an AI algorithm is that it's consistent. Once it's trained, it's always going to make the same calls. It's not just replicating what pathologists can do. I think what's even more exciting is to do things that the pathologist cannot do, which AI seems to be possible to do. So if you're just, for example, counting the density of cells, you can do a pretty good approximation by a pathologist. But then there could be much more complicated spatial arrangements that an algorithm can capture, which is almost impossible for a human to do. And so we're doing a lot of exploration in that domain to see, can we find more sophisticated spatial biomarkers so that potentially they could just give additional information to the oncologist. So that's a really exciting area which we're working on as well.
Can you just talk a little
Yeah.
bit more about some of the things that are AI
Yeah.
is helping you do that were a bit perhaps unexpected or not part of the original plan?
Oh yeah, one thing is just that the whole slide image are very large. They could be like sometimes even 400,000 by 400,000 pixels. So that's a very large image. And you could have 600,000 cells in one image. So with an AI, it can literally look at every single cell, classify what kind of cell it is, can measure the distance between all the different type of cells. But that's impossible to do by a human because you cannot count 600,000. Like a human pathologist probably has maybe 5 to 10 minutes to do all the analysis on one of these things. But with these computers, you can, you can look at everything in maybe our really optimized algorithms can do it in about 15 minutes. Just look at every single cell and make these kind of predictions. And then there are also situations where actually for certain things that you want to predict, there's no human recognized features for various sort of molecular predictions. Like if you have this kind of gene expression, then it means that your cancer is more likely to reoccur. So usually people would do maybe some kind of genetic test, but that could be quite expensive, could be cost thousands of dollars. So the pathologists cannot see it from the slide because they don't know what to look for these genetic tests. But potentially we can do this using AI because we know this patient has this genetic expression, and then we can use AI to say you can just look for any features you want in here and then just try to predict. And we've done some experiments like that, and we can get some pretty good results, like 80 or 90% accuracy. And if we ask the pathologists, they would say they don't know what to look for. So there's another example of using AI to predict things that pathologists cannot do.
Can you just talk a little bit more about what you think the end outcome of having some of these AI tools in the hands of oncologists and pathologists might
Yeah.
help us do? What are some of the things that we might get out of these sorts of tools?
I don't think they should be replacing pathologists. I think reliability of prediction is really important. Pathologists are human, so they're going to miss things. I have a colleague which is working on this early stage breast cancer where the tumor might be tiny, right? Imagine looking at through 600,000 cells and only 10 of them are actually the tumor. The rest is just other stuff, other kind of cells. And it's very easy for pathologists to miss that kind of thing. So using AI, you can literally look at every single cell, is that a tumor or not? And then you could then give that to pathologists to double check. So it's really a way of just quality assurance, I think. And because you have this quality assurance, the oncologist will have more reliable information to make their decisions. And yeah, so I think it would also just make it more efficient for pathologists. So instead of a pathologist can only get through 5 cases in one day, maybe they can get through 20 cases in one day. It's more capacity and means that people can get their results back quicker. With cancer, you want to know what's happening as soon as possible. And if you only have this number of pathologists, then if they can work faster, then it will mean you get quicker results.
I completely agree. Do you think it also can support like earlier diagnosis if it can see much more detail?
Yeah, I think that will be the case. And I think a lot of the early diagnosis is actually probably a bit more on radiology. So when you do for breast cancer, I guess chest x-rays and also MRI, T scans, you can also find tumors and things like that in those kind of radiology things. So for the radiology, what's interesting about radiology is that basically everything's digitized already because the radiologists basically look at a computer screen, looking at the images. So it's already digitized. And that's why AI applied to radiology is much further along in terms of adoption in industry. And whereas this is something I haven't mentioned in pathology, although the AI technology is there, but it's almost very rarely applied. One of the major obstacles is still that most of it is not digitized. So most of it is just you have a tissue and somebody looks at it under a microscope and they never scan it. So that's the first sort of barrier you have to overcome before you can apply AI. You have to be able to scan this, store it in some kind of database, and to be able to retrieve it, and so on. So the hospital needs to update the IT system to support this. As far as I know, this is one of the problems at the moment still. They need to invest to have that digitization.
I think that's such a great point, that it takes time for people who are in these specialist roles that haven't been working so digitally to date to
Yeah,
get up to speed with that. And plus they have to learn new equipment and et cetera, et
yeah.
cetera. How would you suggest somebody, if they're in bioinformatics or pathology or hematology or any of those sort of specialist areas, what's your suggestion for where they start to build some of their capabilities so that they can better work with AI tools when they get access to them?
Yeah, I think one idea would be to work with maybe researchers who have this kind of experience and for them to talk to other pathologists who have used this kind of software. There's two broad categories. One is open source and one is proprietary. So the proprietary ones are probably easier to use because the good thing about them is as long as you pay to buy the software, then they have sales representatives. They provide support. So that's really important. And the people who are providing support, that's their job, is to help their clients make use of software. So I would say that probably that's the easiest starting point. There's companies that do this now. Reach out to these companies, get their sales representatives to come and present their software and then just try it out. I think maybe not sign up for anything straight away, but just try it out.
Just play. Oh, that's such a good idea. Just
Yeah.
get some people to present and see what's out there and play with it. Really great example. Yeah.
Yeah, I think so. So the other thing is if you want to work with open source software, then it's probably better to partner with academic like us. We know the open source software. We've actually making some of our own. And also, for example, there's a software called QPath, which is open source digital pathology software. It has very rudimentary AI, but it's a good user interface to be able to load up a slide, visualize it, annotate, do all sorts of things. You need to be familiar with that software base. And then so there's open source software out there, but the bad thing about them is that they don't come with their own support. So you have to play around with it yourself, and it's a bit harder. So it's good then you can partner with an academic group and maybe get some help that way. Yeah.
That's such a good idea. And so talk to me about when you're partnering with academic groups. So let's say somebody was wanting to partner with you or others. What does that process look like? So how do they engage? What are some of the things that they should think about?
So there's two kind of academics that you can engage with. One is ones like us, which have already experience in digital pathology. But I think there isn't that many groups like this in Australia. More generally, there's a lot of people who are working in computer vision in general. So if you were to do that, then you could reach out to the university. They have an industry liaison people. So this is how we got contacted with the people in Austin Hospital, is that they contacted our industry liaison sort of group, and then that person knew me, that I work in computer vision. To be honest, at the very beginning, I didn't know anything about this stuff. The first time I had a meeting with the pathologist, I could literally only understand 20% of what he was saying, to be honest. So I personally had to spend time to learn the biology. I had to literally go on to Khan Academy and do some of the high school biology classes. Like,
I love
and
it.
then,
Yeah.
and then I got my students to do that as well because the supervisor doing it, they have to do it too. And then I could start to actually understand what they were saying, to be honest. As an industry person, you need to be a bit patient and talk to people who are sort of academics who are committed to working with you. I think that one is put the actual time in. But so that was at the beginning, but towards the end, maybe 2 years into it, I could basically understand pretty much everything, like 80 or 90%. I was really funny was one time I was introduced to this new oncologist, and then she had all of this really cool data. And then I was just on an online phone call, and then They introduced me, and then I think she just, oh, it's just a computer science guy, probably doesn't really understand like what we're talking. And then the pathology oncologists kept talking to each other about the project. And then basically I could understand everything they were saying. And then I started to say, oh, actually you can use AI to do this part. And then they were really surprised, like that firstly I could understand what they were saying, and then I could say why AI could be used, and then they just stopped and they asked, me questions, and then I started saying, yeah, we could do this, blah, blah. This is how you could do it, and then you need to create this kind of data set for me and all of this. After that, it completely shifted to AI, that whole conversation, and they just became really excited. But if I didn't have the background knowledge, I wouldn't be able to understand what they said. So yeah, it takes time. Yeah.
I love that story. That's so cute.